hopefully you can see the cover slide there. But really, I often present, this is a cover image, and it's the image that I want to, I guess, the takeaway message to come out in my presentation today about the value of using finer soil particle size and fine soil fractions in exploration geochemistry. And it may seem strange to have a picture of a football field and relate it to soil geochemistry, but hopefully as we go through this presentation, you'll understand where I'm going with that and why it's important. It doesn't have to be Optus Oval as this state, it could be any football field, but you'll see as we go through why that's important. And Optus Stadium is obviously quite close to where I am. And while I will talk mainly about fine soil fractions, and in particular something that CSIRO has developed myself with my team called Ultrafine Plus, that will be the center of my talk and most of the latter part where I think we're going with exploration geochemistry and how we can advance it. I want to acknowledge right up front that, you know, it doesn't work everywhere. It's not one of these silver bullet type approaches. There are, and I would recommend, you know, horses for courses, and coarse soil fractions in some settings can be very effective. So a good example I've got there, the bronzewing discovery in the Yandal belt was done with piezolyths and near surface, again, fairly residual type soil settings. But in that region, if you understood that, there'd be no reason to go to a fine soil fraction. You know, when you have something that you know works very effectively, use it. Don't switch tracks just because you've heard, you know, this presentation or some other thing touting how good it could be. It's all about understanding your site and your setting. Where I think, and hopefully you'll see as we go through this, where I think we add value is making it easier to interpret your geochemistry and also making it easier to understand your landscape and your setting without perhaps being, you know, an expert in regolith geochemistry. So I would say know your site is really important. So orientation work is always valuable. And, you know, the little plot down the side there, I think, is of, I think that's from Kalahari Sands, actually, in Africa, you know, where, you know, if you're looking for perhaps lead, the fine fraction is obviously giving a much stronger signal in the less than 2 microns. But, you know, most, in this case, they were looking for copper. And, you know, that medium-sized fraction and the sand size fraction was actually quite an effective particle size to work with in that environment. And the other thing that, you know, I would say up front is marry the best sample media with your analytical technique. And I pinched this from one of Nick Oliver's short courses where he talks about combining, I think it's assays actually, with the right instrumentation. So, you know, picking the wrong instrumentation, you get the Mr. Bean across the poor sample media. So this is the coarse or just sand size fraction in this example mainly. You know, you are going to get the Mr. Bean type geochemistry with, you know, something that's probably quite comical in many respects, because you're not going to get the, although, you know, it might be quite sad also that you're not getting the value out of your sampling and analysis. And, you know, Nick talks about, you know, what you really want in a Hollywood setting is something like George Clooney in his Corvette. You know, you pick the right instrumentation, you pick, you know, the best sample media you can work with in that setting. And so this ties into that orientation type work that I mentioned. So understanding, you know, where you get your Corvette from, or which vehicle you're looking for is important right up front to get that sort of high quality geochemistry results. And I think in the past we've kind of been a bit stuck in our ways. And he also reflects on, if you mix these up, you're also going to get poorer quality results. So, you know, picking the best size fraction, and so maybe the ultra fine soil fraction is really good, but if you're measuring it with the wrong instrument or using a lab that doesn't have good QAQC and all these other things that you need to consider, then you're still going to get a really poor quality result, not what you're looking for. And the opposite of that is, you know, having the best instrumentation in labs, but picking the poorest sample media. you're going to get reasonable geochemistry. You get George there with some sort of vehicle that works, but it's not nearly the slick sort of geochemistry that you're looking for in your results. And I would argue, and I'll sort of show a bit of an example, that I think over the last 20 years, we've kind of been a bit stuck in this space where we've kind of got on this, we do soil chemistry and we separate out the standard, less than 250 or less than 180. I think that's just 60 and 80 mesh sort of samples. And we assay it for, 30 or 40 elements. And that's not really being questioned, sort of how we can improve it and whether there's reasons that we would want to be improving that. And that leads me to another image that I use quite often when I introduce this topic, and that's the FONS. And there's the idiom that some of you may be familiar with. It's called jumping the shark, and it actually comes back to this exact scene in Happy Days for some of you older viewers that may recall that show. And where that comes from is basically the producers of the show were watching the ratings of Happy Days decline. And so what they did was just pretty much arm wave bigger and bigger. Think of the bigger, more outlandish things that the FONS could do. And in this case, they took him on a water ski and he literally did jump a shark that was in the Californian Bay Area. And so it was just ridiculous, over the top. The show continued to tank and it didn't give any benefit. And I think with a lot of the surface geochemistry over the last few years, I think there's been a bit of this arm waving with techniques and saying, this method can see through 100 meters of cover or 150 meters of cover. I've seen in presentations and websites. And there may be select environments where that does work, but I think often what it does is we've kind of jumped the shark in terms of making these claims without having the science and fundamentals to back up, or even the understanding of the mechanisms. So I won't talk too much about the mechanisms of metal migration, but it's really important to understand where your anomaly might come from and how it might get through that thick cover. If you've got thick cover and you can't make a case for how an anomaly might get up towards the surface, then surface geochemistry is not really going to work for you. And I think Mark Arundel also gives a presentation around this where he talks about the value in the shallows. And I firmly believe that, in that there's a lot of areas in Australia and actually globally where we might have 2 to 20 or even 30 meters of cover. So, I wouldn't consider that too thick. It's shallow cover, where there's a lot of potential for buried mineralisation that we haven't explored very effectively. And I think that's where the real opportunity is for surface geochemistry, in particular, working towards the finer soil fractions, which ties into some of the earlier research we did at CSIRO as part of the Amira P778 project series led by Dr. Ravi Anand. And I was part of his team there. And one of the things that we did just out the back of the building here was take ore material, bury it, and try and study how the material was moving through that environment. We also set up some lab experiments right behind me here in the lab, where we souped up this same type of environment and had heat lamps and fluctuated the water tables in those columns and looked at how those metals were moving through it. And what we found was that you can generate surface anomalies really quite quickly, and really to quite a high concentration if you have the right environment. And what we found from these studies, so on the left here, I'll just get my laser pointer. What we have on the left here is a buried kid play pool. We put the ore in there, and we had, in some times, we had some sampling devices running down into it and surface measuring things. And then we backfilled it, and then we started monitoring over the surface. And what we found that was really quite remarkable was within 7 months, we could actually detect gold above the buried gold ore. We could detect VMS, zinc, copper above the buried VMS ore from Jaguar, which had those elements in it. Now, there were some sites where it didn't work. And what we found was that when we drilled holes in these plastic trays, and it allowed the surface water to just percolate down, we lost our geochemical signature. And what was happening is there was weathering of that ore material, but it was just washing down and further deeper into the cover. So we weren't getting anything at surface. Where we had no porosity in that pool, and we had what we effectively had was a seasonally perched water table, that was where we got seasonal signatures near the surface. So we were getting that evapotranspiration. Some of the plants were interacting with that, moving it up towards the surface. So there was mechanisms moving those metals near the surface through sand dunes, 2 meters in 7 months. And that continued over quite a few years. Now, what that led me to believe in particular was what sort of species or what sort of environments are the metals that we're interested in? What are they moving to? How are they moving? And really, they're likely to be small, they're likely to be mobile, and they're likely to be ionic and charged. And we'll come back to why that links into the fine soil particle size fraction and analysis and making that sort of step change in the near future. But I want to go right back to the start, and this is around the time we were running those experiments and the origin of the ultrafine soil survey, and where it really come from. And for some of you out there, and I hope you're either mentors or mentees for some of the junior explorers, it's really valuable to have those relationships. And where my journey on looking at the fine soil fractions in particular, it came from some of those pit experiments and working with Ravi and co, but it also came from this place, which was the Picos de Europa in northern Spain. And it was on a bus trip there where I was at a geochemistry conference, and I was sitting next to Paul Morris, who's the recently retired chief geochemist for the Geological Survey of Western Australia. And it was one of those times where, he was someone that somewhat mentored me, but also took the time to engage with some of the younger researchers and provoke questions out of them. That's really what he did. And he turned around to me on the bus. He was talking about the GSWA surveys and where they were working in some sand dune country in particular. And his question was really quite simple. He just asked me, he was like, what size fraction do you think we should be working with? They had their standard methods and they hadn't really changed too much. And it was that moment that I just said, I think the smaller the better. And I didn't really think about how small until a bit later, but it came back to really that point of time where we started. And so Paul and I then worked with a student researcher at CSIRO, and he said, here's some samples I have from sand dune country in the back blocks of WA. It doesn't have a lot of gold in it. In fact, most of it's below detection, but we've got a few that do. Can we look at, how do we understand these samples better? And so what we did, myself and the student, Marco Cavalieri, we separated out the finest fractions we could. So we didn't just separate out the clays, so down to about 2 micron by definition. We separated out sub 2 micron, down to 0.2 micron, in fact. And we looked at, the gold concentrations within those. And what we found was that most of the gold in those transported sands was in that fine material. So, the 0.2 and 2 micron fractions, and then there was a little bit in the silt size fraction as well. So this is that fine dry-sieved, you might get to about minus 63 microns, contains some of the gold, but by and large, most of it's here. What was, most important was that most of the gold, most of the sample you're collecting is this bulk material. It's coarse, it has almost very little exchange capacity. And so what that means is, so you're really getting very little value out of the bulk of what you're collecting. So when you're sending in your 2 kilos worth of material, 1.995 or 1.95 kilos of that material is pretty much rubbish, and you're not getting any information out of it for trace metals, and particularly gold, copper, zinc. And when we looked at some of these materials under SEM, and this is actually from residual soil, we see these populations of gold, and they make up the vast quantity of gold concentration within that, even though they're all very small nanometer populations. That's where the bulk of the gold is in this. And so it's that fine material that's being mobilized around. And you'll see there the clays example, which brings me back to the image of the football field, because that 500 to 800 meters of surface area is much more likely something like the football field. So if I had a handful of soil in my hand for an exploration project, if that was clay, the surface area of that handful of soil is something like a football field. Whereas if that same handful of soil is mostly sand, quartz, the surface area is barely bigger than the desk that I'm sitting in, certainly no bigger than the office space that I'm in. And when you think about that, and you think back to those soil experiments that we started with, when we were mobilizing metals up through sand dune materials, those materials, they're little charged particles, they're looking for surfaces to connect with and bind. And this comes back to my early days doing a lot of work in soil agriculture and looking at clays and absorption. And so they're looking for large surface areas. Well, they're pretty clearly going to be the football oval equivalent, the clays and the iron oxides, and to a lesser extent some of the organics perhaps, that have big surface areas and big exchange capacity compared to the quartz sand that you're picking up. And that's what really drove us to develop the technique further, was to say, well, let's refine our sample media to benefit from that. And there were a couple of other things that really were already published about this as well, and referred to gold nuggets and how they can be really problematic. And Dennis Arney presents this in his Explore paper. I think it's 2014. I think I might reference it in the next slide. But anyway, he looks at the Geological Survey of Canada, Yukon Geological Survey, where they did a really large survey of a couple of thousand samples over an area that they thought was prospective at the time, very little exploration activity in this area. When they reassayed those same soil samples, and this was like bulk material, this was their duplicate analysis. It's a complete scattergun. And so what that led to was that the gold results in particular were considered a waste of time. No one had any confidence in those results. And in particular, concerning was what I call the sort of oh crap zone, where, if either you miss a nugget because you get below detection and don't reassay, or you get a really big value, maybe it's up in the ppm range, you reassay that sample and you get below detection. Instantly, you're thinking, could be a nugget, but you could also be thinking, oh, the lab's made a mistake. This is, all our assays are rubbish. It's really hard to have confidence in that data when you do that. So for this example, this was in 2003, nothing happened in exploration space for another 5 years, even though the survey had done this work, until another company came in and they were doing overbank sort of sediments and soils, and they did better quality analysis on that, and they found the coffee deposit and opened up that whole area. So nuggets are not really valuable for our exploration. Now, Dennis Arney went back to these same samples and Bill McFarlane and took some of those same materials, compared a couple of different techniques, but what they did was also compare the clay analysis. And what they found was that while they lost the nuggets, they gained confidence in the data because they could reproduce those geochemical results. So your 40 ppb gold assay came back as 37 the next time. All of a sudden, you now really feel more confident about the samples. And that's the value of the clay size fraction. You lose your big anomalies in some ways, but you get confidence and you get reproducibility. So that's really important. And that was sort of what we tied into the early work here. And this is a poor quality slide, but this is actually published, these materials, and I've got a QR code link in the presentation, and it's right at the end, so you can link to these publications and get more information. But we wanted to know how this would work in WA soils in particular. So we got reference soils from historical samples, and it wasn't just over mineralisation, it was over a broad range of areas. So we got background type regions, and we looked at the gold in those size fractions. We looked at copper and other elements too. And what we found was that while the less than 2 micron makes up a very small percentage of these, some of these, Bentley, Boddington, DeGrusse, you can see some of the Tropicana with some of the areas we worked in. When you actually look at the gold in those fractions, all right, you start to see that most of it is in the clays and what I would say the silt size fraction. So that fine material really hosts a lot of that information that we're really wanting to see. We also looked at refining the technique. So we looked at, how much sample do you actually need? And what we found was that, you don't need to collect 2 kilos of sample. We actually assay 20 grams or 40 grams if it can be a problematic sample. So really, there was no value in collecting huge quantities of soil and transporting, and we could reproduce right down to 0.1 of a gram. We weren't seeing any significant differences with the gold in the assays. We did see minor changes in some of the pathfinder elements, and what these typically came out as, they weren't highly different, but they were slightly different. It was when we had organic rich soil, so things like Boddington, or clay poor soils where they were really problematic to get out. And this was, 5-6 years ago now. We've really spent a lot of time working closely with the commercial lab partner to improve that, and so we don't see even those differences anymore. But there's subtleties there. One of the things we do see is a big increase in the concentration. So we improve the amount of gold we collect by restricting down to those fine soil fractions. All of a sudden, we get rid of the diluting quartz and all that bulk stuff that I sort of said doesn't really add a lot of value, and we get greater concentrations, which has a good effect on not getting many samples below detection for gold. And here you see a comparison of about nearly 2,000 samples, same samples, compared with a traditional aqua regia result. So this, again, you're using the same extraction, but you're not using the finer fractions. So you can see there's an increase in using the fines, and 4 acid doesn't really work for gold. But when you think about other elements you might be interested in, zinc is one example. The 4 acid does better than aqua regia, but it doesn't actually perform better than the ultrafine microwave digestion aqua regia extraction that we use in the technique. So it's designed for gold particularly, but we're not losing value chasing copper and zinc. Where we potentially might lose a little bit of value is in some of the resistate metals. So the resistate elements, so tungsten would be a good example. However, when you actually look closely, the tungsten, has slightly greater concentrations, but we still pick the same sort of anomalous samples. And so we've done a bit of background work in this. There's more to come on this. If you were just chasing tungsten tin, maybe I would recommend a 4 acid approach and potentially a coarser fraction. But you're not actually losing out too much by using the fine soil fractions. And we've done a lot of background work on this. So we've looked at comparison to ALS's clay size separation technique, which you have to send your samples to Canada for at the moment to do. And there's a strong correlation. And not surprising, they're doing the exact same thing we do in the ultrafine technique. We separate out the clays and we assay them. But there is a big differences, and you'll see those coming up soon. We also compared to things like mobile metal iron, which doesn't look for fine soil fractions, but it looks for loosely absorbed metals. So it looks at the exchange processes as well. Maybe a little bit trying to do this, aiming at the same phase with a different approach. And what we see is there is a correlation with gold, although you can see on the axis there, the ultrafine produces 60 ppb gold, whereas MMI is at about 15 on that line. So we get a lot more gold out. We get a lot more copper in particular, and the correlations start to drop off with some of the elements with the MMI, which only has a much more limited range, whereas ultrafine, we report 52 or 51 elements at the moment as part of that package, and I'll touch on that in just a minute. So really, most of the commercial labs are now offering a fine fraction. It might be a dry, sieved less than 63 micron. That's not bad. I think it's pretty close to the sort of George Clooney Corvette style. Analytically, all the labs are very good now. What we do with the ultrafine, though, is do that same thing on the clay size fraction, but we package in more information. And this was something that I was really driven early around, was trying to find how we get more information. So, things like pH and conductivity of those soils. pH, we know, influences chemistry greatly, but we don't measure it in the soil. So when we're trying to evaluate geochemical results, would be nice to know the soil pH. Well, we now report that as part of the technique. So we bolted on all these other bits of information. And I'd say when we bolted them on, we weren't really sure how all of them would add value. And I think we're still in that phase where we're trying to understand the value behind quite a bit of that. So, you know, the particle size distribution is useful. And, you know, you might make that equivalent to Leonardo DiCaprio in his sports car, or Hugh Jackman. You know, we're adding all these extra bits of information. So here we're adding spectral mineralogy as well. So both visible and near infrared has been packaged up in the standard ultrafine plus offering. And now we're also reporting FTIR, which I might have a little bit to show towards the end of the presentation. But that's not the standard commercial offering, but it will be very soon. So, you know, we're putting in all this information. Some of it, we're not really sure how we work with it. And I would argue, you know, Justin Bieber here in his Lamborghini is the sort of information that people of my generation and perhaps older aren't very familiar with Justin Bieber. And we're not quite understanding how we perhaps might use some of the spectral mineralogy information in our geochemistry. But the next generation is much more comfortable with this. They understand using big data. They understand interoperability of data types. Machine learning isn't really foreign. You know, so we're trying to develop the method that will capture most of the information we want and also make it, you know, very adaptable into future generations. And here's just an example that I use quite often, comparing a Geological Survey of Western Australia survey result in the northeast Yilgarn. And this was, you know, 300 samples with only a small percentage of them returning detectable gold. We revisited the survey and reassayed those exact same soils with the ultrafine technique. So again, looking, you know, to put the Corvette into this analytical package. And this was the map that was produced. And you can see that all of a sudden, you know, the only mine in the area, Mount Eureka, is picked out. And this is on a pretty broad, this is on 4 kilometre spacing or something. So you're not expecting really detailed targets, but you're picking out trends. And here you can see, you know, the gold clearly picks out the trends in the mafic, ultramafics, possibly extending up undercover. So it's giving you more information. That's just the gold results. We're not even factoring in all the multi-element space. We're not even factoring in things like understanding pH or spectral mineralogy. So there's a vast amount more information we can get out of the new package and the new sort of techniques. The other benefit that I've found by separating out the fine soil fractions is that we're not as restricted by soil morphology. And this was something that I worked on for quite a few years, was looking at sampling depths and understanding, you know, whether you're in an A or a B or a C horizon in your soil morphology. How does that influence your chemistry? You know, so, you know, do you trust your field crew to go out and be able to identify soil horizons when they're sampling? You know, probably not as critical in some areas of Western Australia, but certainly really critical if you're in eastern parts of Australia and other parts of the world. What we find by separating out the fine soil clay content is that it's not as limited. So even though we might have much less clay in the upper parts of the horizon, we're still pulling out the clay. When we get deeper in the profile and it's clay-rich horizon, we're still pulling out the clay and analysing it. So we're comparing apples and apples. And in the past, what we've been doing is comparing a sandy soil and diluting the signature with, you know, more clay-rich soil, which has a stronger analytical, you know, trace element component. And so instantly, if you get more clay, that's your bigger target or your anomaly. And it's not really related to anything about mineralisation. And so here's a couple of examples I've presented previously where the target, this is gold through this region, and you see it, they compared a number of techniques. We did part of the CSIRO study, and it picks up at multiple depths in the ultrafine fraction. It doesn't pick it up when you do coarser size fractions. It didn't pick it up when we did biogeochemistry. With much more variation in it. And even one of the sites that I've spent a lot of time working on is the North Mytel nickel site, which was blind at surface. But when you got down into that sort of interface zone where the clay starts to pick up, you actually get a subtle nickel signature above the ore zone. And it relates, and we've done profile work, detailed hydrogeochemistry, a whole range of things at this site. And it's linked to the residual weathering nickel below, not necessarily related to the mineralisation, but certainly an enriched nickel in the residual saprolite. And you do pick it up when you look at separating out the clay size fractions, whereas you would miss it if you're separating the surface soils only, without understanding that environment really well. So, what we did was develop a technique and that has, no issues with nugget effect. It concentrates a lot of base metals and target metals. It reduces below detection, and it accounts for a lot of soil changes in soil properties, which is really valuable. And none of this was really amazing or new information. It was just packaged up where it was easy to use. And then we commercialized that with LabWest, who is the commercial partner for us, and offers this as a standard analytical technique now. I've put the QR code in there because that links to the Ultrafine, the CSIRO Ultrafine website. And from there, you can get information, like you can get links to these papers, journal papers. You can get linked to that GSWA's report and some of the newer information that's coming out as well. From the Northern Territory, we've done a report there as well recently. So there's all sorts of new materials there, and a lot more background, frequently asked questions, and that sort of thing. But now what I really wanted to talk about is the next steps and where we've gone with this. And this is a picture of Thomas Kuhn, who wrote The Structure of Scientific Revolutions in 1962. But what he really talked about was paradigm shift. He coined that phrase. And I'm not sure where it's a paradigm shift, but it is. And they use this Wittgenstein diagram as a really good demonstration of that. And what I think we have changed our view on is how we view our geochemical results. And so I think for many decades, we've been looking maybe at, from the left-hand side of this diagram and saying, it looks like a duck. And we've started to say, well, maybe we should look at this differently. Look at these other parameters. Look at the information that we haven't been capturing and how that helps us interpret better. And so, that's the sort of thing that I think is more rabbit geochemistry. So whether you see from which side of this diagram, and that's the shift that I think we're going to. I don't necessarily think it's a paradigm shift. It's just an adaptation of the way we're working. But I like that diagram as a reminder of where we're going. And so the next phase of this work is around the next-gen analytics. So it's how do we interpret those results better? So we combine the soil analysis, we combine spatial data, and we start doing machine learning on it. And we make all the product that we're producing on the other side much more easier to interpret. That's really what it's about. It's not about trying to do some amazing, highfalutin machine learning that only a select few can understand. It's actually about packaging it up so people can use it. And that's what we've done. And I'll gloss over the first couple of points and spend a bit more time on the last one. So, one of the things we do is now, as part of this, and it's not available to everyone yet, but project partners are doing this, it automates QA/QC. So when you submit CRMs and certain CRMs and duplicates, it gives a report back instantly in traffic light colors that you can see how your assays are performing. And we've got a whole bunch of rules around how they work, and it works for some of the spectral data as well. It's not just geochemistry. So you can quickly glance at your data pack and go, okay, that's pretty good. I need to be careful with my zinc results because they're showing more variance than I expect. That's the sort of information you've got straight away. Click of a button. The other thing that we output is all the data comes back in maps, PNGs, so you can quickly look through the images, shapefiles, so you can quickly drag them into your GIS package and produce even better maps. And all this is really done so it's easy to use. We put it in landscape context, and I think that's probably one of the more important factors. And you'll see that in the coming up examples. And then we've got something called the DSO, the Digital Sample Observer, and that's a really easy way to view your results. And so landscape context is where I think we will make the biggest inroads quickly in this environment. And so we've got this sort of typical landform where you might have your survey points, and you can see that you're sampling on a grid, you're sampling over very many different environments. And so, you're likely to pick up, this deposit or this mineralisation showing because it's sitting in a residual setting. However, the other ones you've got are probably unlikely to be picked up, and I'll show how we work around that. So you've got very different environments and different cover sequences. Now, what we've done as the team, really, we've looked at packaging up spatial data layers and interpreting that as a landscape output. It's not quite a regolith map, but it does relate to regolith maps when we do the ground truthing, and it relates to superficial environments and depth of cover. So that's the other thing. We put in a cover depth estimator, which is this valley bottom flatness index, because where the cover gets really thick, that's where you want to be looking for more subtle geochemical anomalies. And so you can see the output there from various spatial learning, spatial data sets. And here's another example where you can see the input layers and the output clustered landscapes. Now, this is one of our early ones, and you can see how that relates to the satellite imagery. When you look at a traditional regolith map, there's not a lot of information there that you can start separating out your samples. So if you've got a grid over here and you might have 30 samples, you might have 300, can you package them up into different landscapes? And, you've got 3D units there in the traditional regolith map, but it's really not a lot of information. Now, why we think this is really valuable is because you can do more things like interpret your anomalies. So here's copper results for the whole population of a survey. And what you're going to find is these are your standard targets. So these are anomalous by definition. And they're also, this is a residual soil unit. And so that picks up this area in this survey quite well. But that's the stuff you're going to find. What you're going to overlook is the more subtle copper anomalies, and these are clearly anomalies in that landscape compared to the bulk of the geochemical results, but they're very low concentrations. And so now we're making those easier to interpret and see. And you can see them sitting all up here in the cover sequence. And also you see a couple of blue ones behind there. So where there's a little bit of cover, you're in a pretty hot zone there for your copper targeting, but you probably wouldn't have got into this area. Some other things that we've packaged up, and here's another example the New South Wales survey's about to release in a report, is looking at dispersion directions and source directions. So we output that as part of the package as well, where we look at the landscape information and say, well, where is this signature likely to have come from? Each of these is per point, so you can see that the anomalous results here are pointing towards the Federation deposit, and likewise this is the general dispersion direction. So this is broad scale type direction. So if you have a deposit here, the dispersion direction is downslope. So that's kind of where you'd be hoping for a geochemical signature, and you actually find one here where you've got a bit of cover. So helping you target better and more effectively. And I've thrown this one in because it just demonstrates where we're going with a lot of our thinking on this. So we're trying to package up stuff and make it easy. So we output principal components, for example, so multi-element indices and things like that, where you can quickly, you might pick principal component 3 as being important because it hosts gold, vanadium, arsenic, tungsten. It's one of the, that's the pathfinder element you're interested in, zinc, and then you get a plot for that and a shapefile, and you can quickly drag and plot it. And that's also showing us, differences with the soil particle size. So you can actually see where your environment is changing in your landscape. You can see where the pH is changing in the plots. These are older plots. They're a bit more nicer produced than these early maps. And likewise with the spectral mineralogy, sometimes you might find something unusual in the mineral spectra that's saying this sample stands out. And it may not be linked to mineralisation, but what we want you guys to start to do is look at the results and say, well, actually, those are unusual samples, so I can work on that. These are standard targets. I've coloured these dots by PGE. This is a PGE kind of exploration effort. And all of these samples are brightly coloured because they sit up in the landscape. Where they're in the depositional settings, they're grey, they're not so exciting. But if you start to look at them, these are the ones that stand out from the rest of the population. These are those unusual potential targets. And that's all we're really trying to do is change the way we're thinking about our geochemistry. And we're still working through that. And one of the most exciting things is the simple way in trying to view this. And this is the digital sample observer. Here you see quickly the spatial input layers that produces a clustering map. So this is a very big survey. You'll see that in a minute, and this is why I'm not trying to run it live off a web server, because it just goes very slowly. These are just snapshots from the web viewer. And you can see here you've got a couple other layers. This is the model it produces. These are the surface geology maps from the surveys that we sort of bring in. And then you've got some other information down here just for ease in trying to interpret your geochemistry. Now, when you actually look at the results, you've got tabs on the right-hand side here, and you can quickly click on those and look at, the zinc concentration. What you see in this survey, which is many thousand samples, is that there's one statistical zinc anomaly when you look at the whole, or two, when you look at the whole population. However, when you start breaking that down by landscape types, and we have quite a lot of landscapes in this because it's a very big survey, you can see there's, by landscape type, there's actually now quite a lot of, or a number more potential targets, and some of them actually cluster together. You can quickly zoom in on those, like this, and you can see instantly, if you were trying to do this with a regolith geology map, you're getting almost no information. Actually, no information for that. However, on the clustering algorithm here, you're seeing the different landscape units and how those relate. And all of a sudden, these ones in particular, even though they weren't anomalous on the whole, by landscape type, you've got a pattern through there, and that makes a really viable target. And you can hover over them in your survey, and it'll tell you the concentration, the sample ID, which cluster it belongs to. And you can see quickly that there's a big difference between 600 ppm zinc and 116. So you probably wouldn't pick that 100 as being anomalous, but once you start separating it by landscapes, you understand that's really the case. And so there's a few other bits of information that you're getting out too. So you can click PCA, the principal components, you can click conductivity and pH and get a map very similar to this. This one is total organic carbon. So again, you can start to see, well, are some of my samples carbon rich? So they might be artificially absorbing more zinc. That's probably a likely scenario. So it might allow you to cross out maybe this target down here as a false positive. All of a sudden, we're starting to think much more about our information we're getting. And that, brings me to sort of the end of my talk, where I want to highlight the two real key images that highlight most about why I think fine soil fractions have value. And that is, the Wittgenstein diagram, starting to think differently about your geochemistry, starting to gather more information and also interpret it differently than we have done in the past and make it easy to work with. That's probably need a diagram for that as well. And then the other one is the football field. So just remember, when you're collecting soil samples, it's about the difference. The soils aren't all the same. And if you have clay-rich soils, you have a lot more surface area than if you have a sand dune type material. So understanding that soil morphology and soil properties is really important to understanding your soil geochemistry for exploration. And I would, argue that in many cases, the fine fractions are probably a good first pass part to start. And I think with the way we're packaging up some of the analytical outputs, we're also making it easier for industry to explore more effectively through cover. And again, just thank the team that's involved in this project. There's a number of them. There's also a team externally at LabWest that are working quite effectively in terms of improving our methods. And I'll just finish with the QR code there that you can scan and get to our website, which has presentations like this in some cases and a whole lot more information for those that are interested. Thank you. Thank you very